Hi there! For this final video of the MOOC, it seems fitting to take another look at the picture that serves as our opening slide. As we have seen before and in the previous video, this is some artwork by the Shoshone Native Americans. We already saw that the length to width ratio seemed to be different from the one in Western European culture. Now, in the same anthropological article where the Shoshone data were published, we also find similar data for the Crow Native Americans. We have 20 and 12 observations respectively. A natural question to ask is then, do the length to width ratios for these two tribes differ? Well, the difference in means is 2.37. But is this large enough to be confident that there is a significant difference? This question reminds us of a two-sample test on equality of expectations. You previously encountered the two-sample t-test, which could be used if normality could be assumed, or in the case of large samples. Since then, the central limit theorem comes to the rescue. Unfortunately, in this example we have neither. The sample sizes are not large enough. We have 20 Shoshone observations and 12 Crow observations. And one look at the QQ plots tells you that assuming normality is quite a big leap. Well, there are other techniques available. One of them is the permutation test, which is a technique that uses resampling. The null hypothesis states that the two samples come from the same distribution. By the way, if this null hypothesis is true, then of course the expectation of the length to width ratio is also the same for the two tribes. Now, this is how this permutation test works. We will put all the observations together for Shoshone and Crow combined. This gives us a total of 32 observations. Then let's shuffle them and divide them into two groups again, both having the size of the original groups. In our case, we divide them again in a group A of 20 observations and a group B of 12 observations. We compute the means in both groups and we look at their difference. Now, what does this tell us? Well, if the null hypothesis is true, then for each such permutation, the difference in sample means between groups A and B will have the same distribution. And now let's do this shuffling not once, but a lot of times. And each time we compute the difference of the means. The general idea is then that we will see if the observed difference, 2.37, is an extreme one compared to the other ones that we obtain in this way. It seems like a good idea to know how many of these reshufflings are possible. Well, this is a counting problem. It actually comes down to choosing 20 elements from a set of 32. That is enough, since those elements then go in group A, and all the other ones automatically go into group B. There are 32 choose 20 ways of doing this. In our case, this is over 200 million. So this is the number of reshufflings, one of which is the original one, where group A corresponds to the Shoshone data and group B corresponds to the Crow data. This would still be feasible. 200 million computations? Well, they take some time, but not too much. However, it's not really necessary. By taking, let's say, 1 million random reshufflings, we will already get a very good idea. Let's see how we can tackle this in R. We have a vector Shoshone containing 20 observations, and we have a vector Crow containing 12 observations. Let's put them together in one vector called both, containing 32 observations. We call S the sum of all observations in this vector both. We will need that in a minute. Then we pick 20 observations from these 32 and we put them in group A. One of the ways to do this is to choose 20 different integers from the set 1 up to 32, and they constitute the vector indices. And then we look at the values in the vector both, which correspond to these indices. Well, this is our group A. We easily compute the sum, SA, and the mean, MA, of these 20 values. Now, there is actually no need to also explicitly make a vector containing the other 12 observations. We only need to know its mean MB, which is its sum SB divided by 12. But SA and SB together are obviously S, so we easily find that MB is S minus SA divided by 12. Our quantity of interest is the difference of these means. For this random reshuffling, it turns out to be 0.79. Now, all of this is repeated 1 million times using a for loop. The only difference in the code is that now we store the differences of the two means in the vector diff. Let's take a look at its histogram. And let's indicate the observed value, 2.37, as well. Here you have it. So now the question to answer is the same as always in hypothesis testing. Was our observation extreme enough to make us doubt the null hypothesis? Sometimes the graphical representation is sufficient to answer this question. In our case, it is pretty clear that the observation 2.37, indicated by the blue line, is not extreme at all. So there is no reason to reject the null hypothesis. If this is not very clear at first sight, it can be useful to also compute the p-value. This is the proportion of absolute values of differences that is at least as high as the one we observed. We consider the absolute value here because we consider 2.37 and minus 2.37 to be equally extreme. To get an exact value, we would need all these 200 million and something reshufflings. So let's approximate it by the fraction we observed in our 1 million reshufflings. Well, out of the 1 million reshufflings, almost 600,000 give the same or a greater difference. So this fraction, 59.78%, is our approximate p-value. Indeed, it is an approximate p-value since we only took 1 million reshufflings out of the possible 200-something million. Just to be very safe, we computed the exact p-value as well. This goes in completely the same way, but now you don't choose the reshufflings at random, you just go through all of them one by one. It just takes some more computation time. This procedure gave an exact p-value of 59.74%. So our approximation was very good. As you probably would expect, right? Given that 1 million is already a very decent size. Our conclusion clearly remains the same. The large p-value indicates that we didn't have an extreme observation at all. So this test gives us no reason to doubt the null hypothesis. Well, this concludes the final video of this final week. It's been a pleasure talking to you. Bye.